So let us say, and I guess this is an example within an example. Let us say that our S is equal to 0.00, I'm sorry, 0.999. In other words, our epsilon is equal to 0.0001. Incidentally, let me ask this question. Let me sidetrack a little bit. Consider two numbers, 0.9, another number 0.9999. Would you say that these numbers are about the same?
No.
Why not? They seem that's sort of approximately 1, right?
No.
So what do you say they are not same?
It's different. It's 0.9 and 0.999. It's different mathematically.
But they are close to 1, right?
Well, it's 90% and almost 999% is different to me.
Like it depends on the context. Like when you're looking at very small numbers next to each other, there is a difference. But if they are compared to something big, like 1 or 2 or 3, they would be very similar. So.
Yeah. So yeah, I guess so. Basically, that was what you're sort of saying. That let me put it in other words. So as you guess, 1 is ideal, and of course you can almost never achieve ideal, which is 1. So as you approach the number 1, it becomes much, much harder. So there is an enormous difference in terms of effort required and what you achieve as you get close to 1. So actually, when you are talking about highly reliable systems, it is actually not the reliability value that you should compare, but it's the unreliability, how likely it is to fail. So in that sense, RS equal to 0.9999, we are talking about a much higher level of reliability compared with if you had reliability just 0.9. So, and let us say your RM is simply 0.9. So how many of the units you need? And if you plug the formula, things in the formula, then you are going to find that X is basically equal to 4. Will give you what you are looking for. So if you have 4 units in parallel with reliability 0.9, then that will give you a reliability level equal to or slightly greater than 0.9999. You have to plug in the numbers and use the calculator. So, but assume. But this is, of course, for an ideal system, right? In actual case, there are other issues that come into picture, which we will talk about later. And in fact, maybe we should talk about them right now. Any questions or comments so far? Okay, now let us look at a concept which is called coverage. And this is not the same coverage we had talked about earlier. We had talked about test coverage, but that's a completely different thing. This is coverage as it is used by people in reliability evaluation. So keep in mind this is a different term. Now it turns out that sometimes there's a term which has a completely different meaning in 2 different situations. And we recently came across a situation. So we were using the term in a paper, vulnerability. And there are actually 2 different meanings of the term vulnerability. So the reviewers, they had some confusion because they're in the literature on risk. There's a term called vulnerability, which is something which is an attribute of a system. And then in software security, there's a term called vulnerability, and you talk about one vulnerability, two vulnerability, or this vulnerability was discovered today, and so on. But sometimes if you put them in together in the same document, it gets confusing. So this coverage is not the same coverage as test coverage, but this is coverage in terms of reliability or fault tolerance. So let us assume that we have a system where we have two units. Let's call them U1 and U2. And one of the units is the active unit. So this is your active or primary. And this is the secondary, or we could call it the backup. And basically in some situations things work this way. You have a primary unit which is functioning. You're relying on the primary unit to work. If the primary unit fails and you detect the failure, you switch over to the backup, the secondary. And the question is, what is the reliability achieved in such a situation? So let us calculate that. So the system reliability in this case is equal to probability that U1 is good plus, if U1 is good, then no problem. It doesn't matter what U2 is doing, because U1 is the only one that is active, right? But in case U1 has failed, you have to consider a second term. Oh, I'm using P for probability. P probability that U2 has taken over, given U1 has failed. Now I'm abbreviating, so my sentences are not grammatically complete here. Probability that U1 has failed. Okay, how does this look? Do you agree with this? Probability that U1 is good, or if U1 has failed, then probability that U2 has taken over given U1 has failed. And we can write that as reliability of 1, this is a reliability of 1, plus, let us assume that we can write this as R2C, and I write this as 1 minus R1, 1 minus R1. So here, probability that U1 has taken over successfully, given that U1 has failed, is given by R2 multiplied by some coverage factor. So this is the coverage factor. And basically, this coverage factor accounts for the possibility that failure may not have been correctly recognized, and also accounts for the possibility that failure may not, that the switch over may not have been successful. Maybe there was some problem during switching. So C, ideally you would want it to be equal to 1, but it could be less than 1. And in general, I could say that in general, why don't I do that here? So I can generalize that in case you have multiple backups. Now we are talking about the case with imperfect, incomplete coverage. That means considering the possibility that so-called coverage factor there may be less than 1, in general, we could say that Rs is equal to Rm equal to 0 to n minus 1, because let's assume you have n units, one of them is the primary and the rest of them are backup. Coverage factor for each of them, for each situation, which you may have to calculate separately. Now here's an illustration. Let us assume that R1 and R2, they are both equal to 0.7. And let us see what happens in that case if you change the coverage from 0 to 1, and here's the reliability. And here, let's assume here is 0.7. So if your coverage is 0, your reliability, even though you have 2 of them, is essentially equal to that of in one single module, which is 0.7. And it would rise linearly, the coverage, and it could go up to 0.9. As you can figure out by plugging in the numbers. So as the coverage increases, your reliability would increase. And this basically shows that this is the best case and this is the worst possible case. And that depends on the value of coverage. That would depend on your design. Any questions or comments? Okay, let us come back then to our classical combinatorial reliability. And let us consider so I have mentioned about parallel system where if one unit is good, the system works correctly. But how do you decide which system is good, which unit is good? Now, in some cases, you can have a voting scheme. You can have a number of copies of the system. You can take a look at their output and take a vote. And if anybody disagrees, you know that that unit is bad, right? Because majority is usually right, right? You don't seem to quite agree with that. How many of you said that majority is usually right?
Usually.
Okay, how many of you said majority is right in most of the cases? Okay, how many of you said majority is usually wrong?
Because yeah, exactly.
Now, if you have studied about the stock market, it turns out that if you look at sentiments of the investors, and that turns out to be a very good indicator. When most of the inventors are very optimistic, that is the time you should sell. And when everyone is pessimistic, and everything thinks that they should sell, and they go ahead and sell, and that's of course the time to buy. So remember when the time that, I don't know if you remember that, President Obama, when the stock market was, stock market had crashed, and Obama, he had said that people should buy stocks. But that was actually a good time to buy stocks. And of course nobody believed him because everyone was so pessimistic. But he was right.
Did you buy stocks?
Unfortunately, I didn't believe him. So I wish I had. But actually, I did.